My work will be on throughput. Like Partha, I work in the Compilers, Libraries and Performance Technologies group based out of Menlo Park. I'm not a compiler person, but I work very closely with them. And this is related work to see what architectures do, essentially before you get hold of them. All right, let me do it like this. So let's get started. I have an awful number of slides. So I'm on a tight schedule, especially thanks to Conrad's warning. Oh. No, that's better. That's better, thank you. I just hate those microphones, and I guess it's mutual. I'll get started straight away. Okay. As Partha already explained, with UltraSPARC T2 or Niagara 2, it gets interesting for HPC. The T1 was like okay for some HPC applications, but it was quite a narrow market. With T2, we think there's much more potential, and I'm going to again show you some data on that. It's fairly early work. I have to admit that I need to gather more data, and I also need to better understand the characteristics of the applications that I've been running. Because I have my own test suite, and unlike spec, I don't have a battery of people I can throw at it to understand it. I got to do it all by myself. So I'm just going to show you the data. I know these applications fairly well, but again, they haven't been as well studied as the spec benchmark. I have 20 applications currently. It's growing. Luckily, I don't have to live by the rules of spec. That's an advantage. I can just add applications as they cross my path, and I think they have some value to add. They're pretty much, all of them are user-based. They reflect what you are doing. In some cases, I cannot get the full application, but then I could write a kernel that reflects, that captures the key computational behavior. And they cover the usual HPC range, mathematics, physics, chemistry, written in Fortran and C. There's one C++ program in the wings, but it's not integrated yet, but maybe next time I can add that to my list. They stress the CPU and memory side, so there's no I/O. That's the disclaimer. This is pure CPU memory bound, which is still very important for a large class of customers. They've been reasonably well tuned at the compiler level, but not very extensive. For those of you familiar with the Sun Studio compilers, about all of them are compiled with -fast. I played a little bit with prefetch, maybe throw in one or two more options, and that's it. And I also have different versions of the same program and different data sets and so forth. But hopefully that pretty much reflects what our more sophisticated users do. Okay. The system that I used was a early beta system that the University in Aachen had installed, and I'm very grateful to Dieter. He sacrificed many, many, many cycles on that box. It was running Solaris 10 and the FCS Studio 12 compilers. Okay. So I'm now going to show you throughput results. In interest of time, I have to restrict it. I have a boatload of data, but if you want to know more, talk to me offline. I don't have a red sticker. Philippe wants to put it on top of my head all the time, but so far I've been able to fence that off. A little disclaimer, this is all discrete data. I have my measured data. The lines are just for orientation. I think it makes it a little easier to read those charts. Okay. The main question is that I'm going to try to answer is how much throughput can I get out of the processor? Okay. And for that, I have to carefully explain what I've measured. So let me do that. Let me take a little bit of time for that. I have 20 applications. Each application may run different versions, different data sets, but one application gives me one timing. That's running all the versions, all the data sets, and I time it from start to end. So when I run one of what I call stream, which has, by the way, nothing to do with the streams benchmarks, I'm just not a very creative guy, I'm afraid. When I run one of those streams, I do get 20 data points. And whenever I show data, it's always run in throughput mode. So it's always run where you start the 20 jobs at the same time. And then, of course, I can run multiple streams. I can do 2. Then I have 40 jobs running at the same time, and so forth. So in that way, I can crank up the load. And every time that I add a stream, I have 20 more data points. Here's the load on the system as a function of time. And I'm showing you, I ran all the way up to 6 streams. 6 streams means that at the peak, I'm running 120 jobs at the same time on 8 cores. I'm quite sure it was silently crying, but I wasn't there to listen to it, so I didn't care. There's quite a high load, and the rest is lower, but still significant. And as you see, over time, things, of course, taper off. But at least for a number of hours, the system was stressed very heavily. This is almost, I think, like art, geek art, I would call it. But it's the memory consumption as a function of time for all those 6 different experiments that I did. I didn't want to bore you with showing one after the other. Just want to give you a feel of the dynamic memory utilization. And as you see, I kind of summarized it. The peak limit is 30 gig. That's what I used. And so I always run up to the maximum memory that I have on the system. This system had 32 gigabyte installed, so I was really pushing my luck. All right, well, I was lying a little bit when I said I only show throughput. This is the only slide with non-throughput numbers because I want to put things in perspective. I want to, in the short time that I've left, take you in a way by the hand and show you the things that I ran into and how I try to solve that. So here are my 20 timings. The purple line are the sequential times. These are sequential, one after the other. This is the best case. I had the whole system to myself and run one job. Okay. The worst case, Solaris will shuffle me around those cores, but as this is a very flat architecture, that's not such a big deal. The blue one is what I measured when I went in throughput. So those are the elapsed times when I start my jobs, 20 jobs at the same time, and just wait for them to finish. My question is, if you would show me this slide, the question that I would ask you is this good or bad? You don't know, so you need to have a reference. You can't really tell. Is one of them like out of line? Is it okay or whatever? Okay. The way to answer that question is the following. When you know the single core times, you can estimate what any throughput benchmark should do, assuming ideal machine and software behavior. So that's the best you can do. And here's a simple example. Let's say program A takes 100 seconds to run, and B takes 200 seconds. And that's what I measured on a single core. Now let's say I'm still on a single core, but I run them at the same time. I start A and B just at the same time. For a while, I'll get half of the CPU or half the core for each application. So I get 50%. That's why A needs 200 seconds of elapsed time to finish, because I only got half of the CPU. When A is done, B has progressed for 100 CPU seconds, because it took 200 and A 100. So B still has 100 seconds to go, but at that point it has the whole core to itself. You get 100%. So that's why the elapsed time of A will be 200 seconds and B will take 300 seconds. And if you don't believe me, this is the way it is. And if you still don't believe me, we'll talk tonight, okay? It's not that hard. Because you can extend this, and that's what I did. You can extend it to multi-core designs and an arbitrary mix of applications. As long as you know the mix, and as long as, of course, you know the number of cores, and you need to have the individual elapsed times on a single core. With that, you can do any sort of estimate. So that's what I'm going to show you now. And here's the first result. Again, running 20 jobs simultaneously. And normally what we would see in the past was that the estimates were worse than what you measured. And I'm a very lazy guy. I always blame contention. I never looked into it, but I'm sure there was some contention somewhere, hardware, software, causing the estimate to be better than what you measure in the real world. Here it's the other way around. When you look here, you see what I measure. Let's take this one, otherwise I'll fall off the stage. You take this one, the measure time is better than what my ideal machine with 8 cores assumes to be. That's really strange. I hope I started debugging my tool to make sure that I didn't have a bug, okay? Clearly, the additional threading adds capability to the system. Dennis talked about that. You have these 8 threads per core. They add throughput. Okay. That's got to be the reason. The question is, can I attach a number to that? Can I quantify that? Can I do, and then eventually do comparisons? So for that, I've been struggling with this for a while. I came up with the notion of core equivalent. And again, I'm not a creative guy. I'm open for any suggestion with a better name. Here's what I want to capture. A core equivalent is a core. It's the same core, the same pipelines that Dennis talked about, same FPU capabilities, integer capabilities, but it does not have the additional threading to help me out. So it's like a simple core. But it's the same kind of core as I have in my threaded architecture. So on more simple designs like UltraSPARC 4 and 4 Plus and current AMD and Intel multi-core systems, one core corresponds to one CE because I don't have that additional threading. So the question is, what does UltraSPARC T2 correspond to? Before I can show you that, I have to yet introduce another metric. Here's what I'm measuring, or computing I should say. I measure, for every of my 20 programs, I measure the elapsed time, and I compare that with what I estimate. I compare with what I estimate, assuming 8 cores, 9 cores, 10 cores, and so forth. That's my CE, so that's the parameter. That average depends on CE. Measured is what I measure. That's the one and only truth. Estimated is what I think it should be. And the best, so you can draw a curve, this thing as a function of the assumed CE, and the best one that I think I should take is the one with the smallest positive value. And that number, that's my throughput number that I want to attach to that kind of throughput experiment. And again, in my case, I had 20 applications. All right, this is just taking a little while, I think. Let's see. Yeah, okay, so here's a graph, and I'll take a few minutes, although Conrad is counting down very heavily right now. I'm on the stage, you're not. So you got 20 programs here, so I got 20 data points, but it also means that I start with 8 cores there, and as I run 20 jobs maximum, it doesn't make sense to go beyond 20. When I would assume like I had 30 cores, it doesn't matter because I still have 20 jobs running. So that's why I stop with the number of jobs. The blue line is that average, that formula that I was showing as a function of this variable called CE. And you can very easily see it should be a monotonic function, and it is. And the first time that it hits the positive value is at 15. And the difference between 0 is only 3%. 0 would be like pretty much like a perfect fit. The maximum, you could also look at the maximum relative difference that you have, or the minimum. This one is too pessimistic, this one is too optimistic, I think. Okay. And again, if you want to know more about this, we can talk about this offline. Here's what I got. So when I assumed that my system had 15 of these CEs instead of 8, I get a way much better fit than what I had before. The numbers are pretty close now. And then once you have that, you can generalize it, extend it. So I'll do this a little more quickly. You can go to 20, 2 times 20, so 40 jobs. Again, when you assume you only have 8 simple cores, you're way underutilizing the architecture. The difference actually gets bigger between what you measured. So the machine is doing better under a higher load. You repeat the kind of analysis, and now my methodology spits out 24. That's the result for this, this throughput experiment. And the difference, so the difference compared to 0 is less than 2%. So I'm quite close. And again, you see here, there's a much better match with what I originally assumed with 24. Okay. Well, I won't bore you to death with all the results that I have. Just for the fun, here's what it looks like if you go up to 120 jobs. And the best value that I came up with there was 33. And you see the good fit with that compared to what you've measured. Okay. Here's the summary. I ran all the way up to 6 streams. This is the maximum load on the system. And what you see, it ramps up and then stabilizes at around a little above 30. And I haven't done the analysis yet, but it's probably not coincidence that you hit the peak at around 60, because you got 64 threads. Maybe it is coincidence, I don't know. You never know, of course, until you do the detailed analysis. So that's one thing you see. Compared to if you wouldn't have the threading, you would lose a factor of 4 in performance. In other words, the extra threading gives you a factor of 4 better throughput. The other thing that I think is very impressive is this is a huge load on that one single chip, and it doesn't degrade. It could degrade. Potentially you could see a lot of degradation and contention and the number going down because the system doesn't like it. So it's holding up very well. And basically that was the story. So my summary is that the threading definitely helps. For what I did, the work that I did, the threading gives me about 4x performance compared to the non-threading, and it behaves very well under very high load. And that was what I had. Thank you. Any